Hi guys, and welcome to this virtual lecture course on electromagnetism. My name's Dr. Andrew Mitchell, and in this lecture I want to talk about magnetic field effects in and near magnetizable materials, as well as the properties of magnetic materials themselves. In the last lecture, we looked at magnetic field effects and magnetostatics in free space. We saw how the Biot-Savart law and the Ampere law could be used to understand how magnetic fields are generated in a region of empty space due to steady flowing electric currents. In this lecture, I want to see how that changes in the vicinity of a material which can be magnetized in the presence of a field. The total magnetic field is therefore a combination of the applied field plus that due to the material's response. Maxwell's equations still apply, of course, but to this total combined field. So how do we treat such systems? I also want to talk about magnetic materials, for example, ferromagnets, which are permanent magnets, such as iron, cobalt, or nickel. How and why do these systems develop magnetization and stay magnetized? How and why do they lose their magnetization when we heat them up above the Curie temperature? I'll also discuss diamagnets, such as gold and copper, and paramagnets, such as aluminium and platinum. These are systems that only become magnetized in the presence of a field, but then relax back down to an unmagnetized state when the field is switched off. Okay, let's get down to work. Magnetic field effects in and near materials can be quite different from the magnetic field effects in free space, because the materials can themselves become magnetized. So what is magnetization on a microscopic scale? Well, magnetic dipoles are induced in the material and then become aligned. So the material overall has some macroscopic magnetic dipole moment. But how are these magnetic dipole moments induced, and how do they become aligned? Well, there are various magnetic materials that we might wish to consider. The different classes can be broadly grouped into ferromagnets, diamagnets, and paramagnets. So let's first start with a quick discussion of ferromagnets. Ferromagnets are permanent magnets. This means that a ferromagnetic material might become magnetized when placed in an external or applied magnetic field, but then when the field is switched off, the material retains its magnetization. Magnetic materials, such as ferromagnets, can also develop spontaneous magnetization. In fact, the magnetization shows the phenomenon of hysteresis when changing the magnetic field. But in all cases, the magnetization is lost once the material is heated up through the Curie temperature. The classic examples of ferromagnetic materials are iron, nickel, and cobalt. However, alloys of ferromagnetic metals can also be non-magnetic, for example, stainless steel. And indeed, alloys of non-magnetic metals can be magnetic, for example, the Heusler alloys. The microscopic origins of ferromagnetism are complicated and depend on the details of the chemistry of these materials and ultimately the quantum condensed matter physics of these materials. So next we'll discuss briefly diamagnetism. Diamagnetism is actually a quantum mechanical effect and is present in all materials. When it is the dominant contribution to the magnetism, meaning when there is no paramagnetism or ferromagnetism, we call such a material a diamagnet. the induced magnetic field in a diamagnet is in the opposite direction to the applied field. And this has the important effect that a diamagnet is repelled in a magnetic field. It is quite a weak effect, and indeed the strength of the induced diamagnetic field is linear in the applied field. And classic examples of diamagnets are copper and gold. Also, superconductors are of course very strongly diamagnetic due to the Meissner effect. Now, what about paramagnets? Paramagnets are materials whose magnetization induced by an applied field is parallel to the applied field. Paramagnets are also attracted by an externally applied field. This, of course, happens because the induced magnetization produces an induced magnetic field, which augments and strengthens the applied field. Paramagnetism is generally, again, a weak effect, and the strength of the paramagnetism is typically linear in the applied field. So in both diamagnets and paramagnets, we have linear materials where the induced field is linearly proportional to the applied field. The constant of proportionality is the magnetic susceptibility, chi-m. In diamagnets, this is negative. In paramagnets, this is positive. Classic examples of paramagnets would be platinum and aluminium. So that was a quick summary of the phenomenology of magnetic materials. We talked here quite a bit about the concept of a material being magnetized. What is magnetization? Well, from the classical field theory point of view that we'll be taking in this course, magnetization is itself like a field, and we will refer to a magnetization field. What do I mean by this? The magnetization field, which I'll describe as capital M, is something that exists everywhere in space, so I can give it an argument r vector. This thing is the dipole moment per unit volume. So if we want to know what the dipole moment at a given point in space is, we just have to multiply by the volume element. And notice that this object is a vector field. So we expect this magnetization field to be non-zero inside some magnetized object. And the idea is that this magnetization field is kind of like a macroscopic or classical field, because we're not considering individual dipole moments for individual atoms or orbitals or electrons. We're considering something that's kind of like a smeared out or averaged field. It is something that's continuous throughout space. So what is this magnetization field, and where does the magnetization come from? Usually we think of magnetism as being the result of moving charges or currents. But what does this mean for magnetic materials? For example, if we look at permanent magnets, such as iron, these don't appear to have flowing electrical currents in them. But actually, on a microscopic level, we have electrons in atomic orbitals in the material that are always in continuous motion. So in some kind of crude classical approximation, electrons are sort of orbiting their nucleuses in orbital paths. And these are kind of like very, very small, tiny current loops, electrons circulating round in loops. So one can imagine that these electrons circulating around in atomic orbitals are kind of like small circuits which produce magnetic dipole moments. And they're so small that they're essentially perfect dipoles. But that's not the only contribution to magnetic dipoles, because electrons also carry intrinsic angular momentum. So there is also a magnetic dipole moment associated with the electron's spin. This is an intrinsic property of the electron, deriving from its fundamental quantum mechanical nature. In fact, that's a relativistic quantum mechanical effect. So there are kind of two sources of magnetization, if you like, magnetic dipole moments in materials. One from orbitals, the electrons circulating in orbitals constituting tiny electronic circuits, and also from the intrinsic magnetic dipole moment of the electron. Magnetization of a material is created in rather a different way from the intrinsic spin of an electron and from the electron circulating around in atomic orbitals. And these different mechanisms give rise respectively to diamagnetism and paramagnetism. So the way that we think of a magnetized material is that it's being made up of tiny atomic scale current loops with aligned orientation. So in this cartoon here, I imagine that I have some material and there are microscopic dipole moments associated with these tiny current loops. And these tiny current loops are supposed to represent either electrons circulating around in atomic orbitals or the intrinsic spin-angular momentum of the electron. So either the magnetic dipole results from an electron in an atomic orbital making a tiny current loop with which we can associate some effective dipole moment, or the microscopic magnetic dipole moment comes from the intrinsic spin-angular momentum dipole moment of the electron. So however it's created, the microscopic magnetic dipole moment m per unit volume, d tau, is precisely the magnetization field. But how is this magnetization field induced by an applied external magnetic field in paramagnets and diamagnets? So first, let's have a look at the case of paramagnetism. Paramagnetism is typically the dominant mechanism in materials with unpaired electrons, where the intrinsic dipole moment of the electron can become aligned in the field. To explain this effect, let's for now model the intrinsic magnetic dipole moment of the electron as a tiny current loop, and we'll see what happens to this in an external field. Let's assume that our electron has an intrinsic dipole moment that's pointing vertically upwards. This is equivalent to a tiny current loop with a current I in the horizontal plane such that the magnetic dipole moment is also upwards. Remember that the magnetic dipole moment for a current loop is the current multiplied by the vector area of the loop. Imagine that we now apply a magnetic field also pointing upwards aligned with the magnetic dipole. What happens? Well, nothing. But what happens if we now twist or tilt our magnetic dipole moment out of the field? Then we obtain something like this, where the angle of tilt we will call theta. And this theta is, of course, also the angle of tilt of the magnetic dipole from the vertical axis. So if we draw the end-on sort of profile view, we'd see something like this. And all of this is in some magnetic field which is still pointing vertically upwards. So the question is, what happens to this tiny current loop that has a magnetic dipole moment that's not aligned to the field? Well, this tiny current loop will experience a torque that will tend to orientate the dipole moment in the direction of the field. How does that work? Well, we imagine that there is a force acting on this side of the current loop, which I'll call F+, but then there is an equal and opposite force acting on this side, which I'll call F-. So the total force is equal to 0, but there is a torque that tends to rotate this current loop counterclockwise, thus aligning the magnetic dipole moment with the field. The force is equal to the current multiplied by the cross product of the line element with the magnetic field, integrated over the path taken by the electrons in the circuit, which of course is just the line integral around the circuit. If the side length of the circuit parallel to the x-axis is of length a, and the side length of the circuit parallel to the y-axis is of length b, then the force, or the forces F plus minus, are simply given by plus or minus the current multiplied by the field strength multiplied by this length b. The torque, therefore, which acts on this current loop, is just the cross product of the force times the vector distance, and we can simply express that in terms of this angle theta
And that torque is something that acts in the x-hat direction. And this can be simplified a little bit and rewritten as the following. And of course, recognizing the magnetic dipole moment m as the current times the vector area AB orientated in the z direction, we can write this whole thing in terms of the magnetic dipole moment m. And we can even account for the vector direction by writing the torque as simply the cross product of the magnetic dipole moment m vector, cross product of that with the magnetic field. So that's the final result, which is rather a simple result. The torque is just m cross b. And what we see from that, as advertised, is that the magnetic field tends to align the magnetic dipole moment with the field. So this is the dominant source of magnetism coming from the electron spin, since the magnetic dipole moment of the electron is an intrinsic quantity that is fixed in magnitude, and it's only the direction that changes due to the applied field. But paramagnetism comes from unpaired electrons. If we imagine two electrons in the same atomic orbital of a material, then these things must be spin paired due to the Pauli principle. Therefore, they have no net magnetic dipole moment and do not contribute to paramagnetism. So, as a rule of thumb, we require an atom or a molecule in a material to have an odd number of electrons for paramagnetism, such that there are some unpaired electrons which can be orientated in the field. It is actually also possible to have materials with an even number of electrons per atom, where the atoms adopt a high spin configuration. So this is a situation where electrons distribute themselves in orbitals in such a way to maximize the total spin by Hund's rule, and this again allows you to have unpaired electrons which can be orientated in a magnetic field. So now let's take a look at diamagnetism. As I mentioned, this is a mechanism that's actually present in all materials due to the orbital angular momentum. We imagine that the electrons are circulating around their respective nuclei, and this constitutes a tiny current loop which has an associated magnetic dipole moment. And this can be, the orientation of the magnetic dipole moment can be changed in the presence of an external or applied magnetic field. The interesting thing is that through this mechanism that I'll sketch now, the magnetic dipole moment tends to align in the opposite direction to the applied magnetic field. And the big difference between this mechanism and that of paramagnetism that I just sketched is that here we don't have an intrinsic magnetic dipole moment, as one has for the electron, but rather the magnetic dipole moment is something that emerges from the electron cycling around the nucleus, and therefore it actually depends on the velocity of the electron's motion. And the velocity can change due to the application of an external magnetic field, and therefore the magnitude of the magnetic dipole moment can change. And this is something that's not true of the electron. The electron has a fixed intrinsic magnetic dipole moment. So this is the cartoon sketch. We have an electron that's circulating around its positive nucleus with some velocity v, and I'm assuming that the magnetic field is vertically upwards, and that in this initial condition, the magnetic dipole moment associated with the orbital angular momentum is also upwards. So I'm assuming the plane of the electron's orbit is in the xy plane, and the magnetic field is in the positive z direction. For simplicity, let's imagine that the electron is in a circular orbit of radius r. The period of the orbit is therefore 2 pi r over v. Why is that? Because the period of the orbit is the time it takes for the electron to go around one cycle. The length of the path around one cycle is the circumference of the circle, 2 pi r, and the speed is v. So if we now want to work out the associated current, and I put this in inverted commas because of course it's just a single electron, but we can think of the current as being the amount of charge that circulates around per unit time, then we can think of the amount of charge as being the electron, the electronic charge, which is minus E, minus because of course it's an electron, and the electron comes round every time in one time period, which is 2 pi r over v. So there's some kind of effective current in this system, which is minus EV over 2 pi r. We can therefore work out the magnetic dipole moment as the current times the vector area, which is pi r squared for the vector area in the z hat direction, multiplied by the current, which overall is minus 1/2 E r v in the z direction. Okay, but what is this speed v? How is it determined? Well, if we're in equilibrium, it means that the Coulomb force between the electron and the nucleus must be balanced by the centripetal force. So let's first consider the situation without a magnetic field. In this case, we have the Coulomb force, which is the electronic charge multiplied by the nuclear charge divided by 4 pi epsilon naught r squared for a given radius of the orbit r, and that has to be balanced by the centripetal force, which is the mass of the electron times v squared over r. Fine. What happens when we switch on the magnetic field? Well, for a given radius r, we have the same Coulomb force, however, we also have a magnetic force, the magnitude of which is the electronic charge times the new velocity times the magnetic field. And actually, the direction of this force is again directed radially inwards, just like the electronic force, and this is because we have like a cyclotron motion. This total force is balanced by the centripetal force, which again is the mass of the electron times the velocity squared over the radius, but now we have a different velocity. So we have two equations here, 1 and 2, and so what we can do is subtract 2 from 1 and obtain an expression for the velocity v tilde and v tilde is the velocity of the system with the magnetic field. This is the difference of two squares on the right hand side, and so we can write this as v tilde minus v multiplied by v tilde plus v. And if we assume that the difference in the velocity as we switch on the field is small, let's call delta v v tilde minus v, let's assume that this thing is small, then v tilde plus v is approximately equal to 2 v tilde. And then I can rewrite this expression in terms of delta v. And delta v will be equal to E R B over 2m of the electron. So that tells us the change in the velocity due to the application of the magnetic field. We just worked out the magnetic dipole moment, m, for this configuration as minus a half ERV in the z direction, and therefore we can work out the change in the magnetic dipole moment due to application of the magnetic field. This would be minus a half ER delta V in the z direction. And we've just worked out delta V, and so we can substitute this in. And we see something interesting here, which is that the change in the magnetic dipole moment m has a negative sign. So it's in the opposite direction to the applied magnetic field. And so what we've proved here is that by this mechanism, the change in magnetic dipole moment is the opposite to the applied field, which is indeed the definition of diamagnetism. The magnetic dipole moment is trying to line in the opposite direction to the applied magnetic field. Finally, I want to talk about ferromagnetism, which is actually rather different because the magnetism in such systems doesn't require the presence of an external magnetic field. The magnetism emerges due to the interaction between the electrons in the system. The magnetic dipole moments of all the electrons in the system spontaneously order to produce a ferromagnetic state. In what kind of systems can such an effect arise? Since the non-zero magnetization field in such a system comes from the magnetic dipole moment of the electrons, we need unpaired electrons in such systems. It is the spin of these electrons that becomes aligned ferromagnetically. But of course, not all metals do have electrons whose spins can be aligned ferromagnetically because of the Pauli exclusion principle. It's quite possible for the atoms that comprise a metal to have multiple electrons that are all spin paired, so that there's no net spin on each atom, and therefore there are no spins that can be aligned macroscopically in the material to produce a magnetization. One might expect, therefore, that atoms that have an even number of electrons would have all of the electrons spin paired in the atomic orbitals, and then those systems could not be ferromagnetic. However, this is not the case. For example, the most famous ferromagnetic material is iron, that has 26 electrons. So there's something weird going on in iron. We see actually that this is a high spin atom on the lattice with 4 unpaired spin aligned electrons. You might have thought that these 4 unpaired spin aligned electrons could form 2 spin paired atomic orbitals, but that's not what happens. So let's have a closer look at iron. The electronic configuration of iron is that of the argon core with an additional 6 electrons in the 3d orbital and 2 electrons in the 4s orbital. So again, this overall has 26 electrons. Why is it, therefore, that this system has unpaired electrons that can be aligned and therefore create a macroscopic magnetism? If we draw out a table showing the electronic configuration, with the rows labelled according to the principal quantum number, and the columns labelled according to the orbital angular momentum quantum number L, such that the energy is increasing as we go up the table, and the orbital angular momentum is increasing as we go to the right of the table, then we see this configuration. And importantly, you'll see that everything is spin-paired. All of these electrons are spin-paired, except for these 4 unpaired electrons in the 3d orbital. The argon core is this part of the electronic structure. And then the whole thing is what we have in iron. Argon, of course, has no unpaired spins, but iron has 4 aligned unpaired spins. So this is something a bit strange. It appears to be preferential to fill up the naively higher energy 4s orbital, which you can see here is doubly occupied, than to spin pair electrons in the 3d orbitals. So iron, for some reason, likes to have unpaired aligned spins. Why is this? Well, actually, the origin is in quantum mechanics. The propensity to form high-spin systems rather than to spin pair all the electrons is described by Hund's rule. In systems where the interaction between the electrons is extremely strong, because, for example, the atoms are packed very tightly together, the potential energy could be very large. It might be favourable in such systems to minimise the potential energy at the expense of the kinetic energy. And this works by spin aligning the electrons. By the Pauli principle, 2 electrons of the same spin cannot occupy the same atomic orbital. So if the spins are aligned, that means they must occupy different orbitals, as is shown here in the electronic structure diagram. And that means that on average, those electrons are further apart. If the electrons were anti-parallel, they could occupy the same orbitals, and then the spins would be closer together. That means there would be a larger Coulomb potential energy between them. So it is a trade-off between the kinetic energy and the potential energy, and in systems with tightly packed atoms and strong Coulomb repulsion between the electrons, it might be favourable to minimise the Coulomb repulsion, not by having spin-paired electrons, but by having unpaired electrons with the same spin. So this is a very sort of heuristic and hand-waving explanation for the origins on a microscopic level for the ferromagnetic alignment of spins to form high-spin states on individual atoms. But that's not everything we need for a ferromagnetic material. That's something that requires the spins on all the different atoms to be aligned across the whole material to produce a macroscopic magnetization. The propensity for spins on neighbouring atoms to become parallel aligned has at its origin quantum mechanics and is beyond the scope of this course, but it's to do with the magnetic exchange interaction. This is something that we would cover in the quantum theory of condensed matter course, but in this course we will just take it as an experimental fact that in some systems the interaction between neighbouring atoms in a crystal lattice can be ferromagnetic. A paradigmatic model to describe magnetism in materials is the so-called Ising model. The Hamiltonian for such a model is given by this simple expression where the sigmas here are either plus or minus 1. They're simply numbers, and they define the spin either pointing up or down, let's say. So these are classical spins. We are summing over lattice sites, and the angle brackets ij mean nearest neighbours on the lattice. So, for example, we could imagine a 2D square lattice of spins, which I've drawn here, all parallel aligned, and the interaction between the spins is just with their nearest neighbours, which I've denoted here with the red lines. So those interactions have a strength minus j, and the minus here is the thing that's causing the ferromagnetism. If I had plus j, then this would favour an anti-ferromagnetic state. Why is that? Well, if we imagine the situation where all of the lattice sites have spins that are pointing up, that would be sigma equals plus 1 for each of the sites on the lattice. Then in our Hamiltonian, we see here a term which is sigma I, sigma j, and if all of the lattice sites have spins pointing up, that would be plus 1 times plus 1 on each lattice, for each pair of lattice sites. So that gives me a positive number, which I then multiply by minus j, and overall that gives me a negative contribution to the overall energy. The Hamiltonian is, of course, related to the total energy of the system. If we then ask what is the lowest possible energy, which is the ground state of the system, then that is the state where all of the spins on the lattice are aligned, because when all of the spins on the lattice are aligned, then every single nearest neighbour pair has the same sign of sigma, and then overall we have the lowest energy. Conversely, if we had a plus j in the Ising Hamiltonian here, then this would favour an anti-ferromagnetic state where all of the spins were anti-parallel across the lattice. Why is that? Because then the lowest energy is achieved when nearest neighbours are anti-parallel, so one of them is sigma equals plus 1, and the other one is sigma equals minus 1. Then the product of sigma I, sigma j on nearest neighbours would be minus 1. And again, the lowest energy state, which is the most negative one, is the one where everything is anti-parallel. However, in this Hamiltonian, I've explicitly used minus j here to capture the behaviour of ferromagnetic systems. So, in such a system, we know that the ground state must be the ferromagnet. Notice, by the way, that if all of the spins were pointing down, so that sigma was equal to minus 1 on all sides, then that would also be a ferromagnetic state, and it would also have the same lowest energy, because the product of sigma equals minus 1 on one side and sigma equals minus 1 on another side is still plus 1. However, this is not the end of the story, because it's not just the ground state that matters. As you know from courses on thermodynamics, the thermodynamic stability of a phase of matter is not just determined by the energy, but of the free energy. And the free energy, the Gibbs free energy, for example, is G is equal to H minus Ts, where T is the temperature, and of course the most important thing in this equation is that S is the entropy. The ferromagnetic ground state with all spins aligned has a very low entropy. If I were to introduce into this ferromagnetic state some spin flips, where one of the spins, for example, was pointing down in a background of everything pointing up, then this flipped spin could be placed anywhere on the lattice, and that gives rise to some disorder and a higher entropy. So if we're not looking at absolute zero of temperature, T equals 0, but rather finite temperature, then these entropic contributions matter. And you can see immediately that at finite temperature there will be some propensity for these spin flips, and as we go to higher and higher temperatures, these spin flips will proliferate and the overall magnetization will be reduced. Now, actually, what happens in such systems is that at a critical temperature, which is called the Curie temperature, the magnetization drops to 0 and vanishes, and then we have a totally disordered state where all of the spins are randomly aligned. So what I want to do now is do a short calculation, but a concrete calculation, for this Ising model to show you how, as we increase the temperature, the magnetization decreases and actually vanishes at this critical Curie temperature. The full solution of this classical Ising model is a bit complicated, so instead I will use a simple approximation called the mean field approximation. The basic idea of mean field theory for the Ising model is that instead of taking into account explicitly the correlations between each pair of sites on the lattice, instead we'll consider that each site on the lattice sees some kind of averaged or mean magnetic field or magnetization due to all of the other sites in the lattice. And we'll assume that this mean field is homogeneous in that it's the same for every single site on the lattice. So there's some kind of self-consistency here. Each site of the lattice sees a mean field from the other sites, but those other sites are also subject to the same mean field. So the mean field approximation is to assume that the fluctuations of the spins, this is the sigma I and the sigma j, around their average value is very small. So we'll let the deviation of the spin delta sigma I on a particular lattice site I, we'll let this be the spin on site I, sigma I, minus the average value. So now our Hamiltonian can be written in the following way. The average value of sigma I multiplied by sigma j plus sigma I multiplied by the average value of sigma j minus the average value of sigma I times the average value of sigma j, and then plus this term with the deviations delta sigma I, delta sigma j. So how did I get this? Well, let's consider this term first. This is the product of the deviations. If I were to substitute this expression in here, I would find that there was a term sigma I, sigma j, and that's actually the original Hamiltonian. Then there's a term plus average sigma I times average sigma j. That doesn't appear in the original Hamiltonian, so we subtract it off here. And then we have cross terms, which are minus sigma I average sigma j and minus average sigma I sigma j. Again, they don't appear in our original Hamiltonian, so we have to add on those contributions to cancel it. So this is an exact expression of the Hamiltonian, and in the mean field approximation, we neglect this term. In mean field theory, we assume that the correlations between these fluctuations is small. And what we're left with is a mean field Hamiltonian which is therefore this thing. And the crucial thing about this Hamiltonian is that it doesn't involve explicitly the correlations between the spins on neighbouring sites. We only have the correlations entering in through the average spin on other sites, or the mean field, if you like. So this Hamiltonian has sort of become diagonal, if you like, in the site's label, which is why this is a nice approximation. Now, what is the magnetization of such a system? In particular, let's look at the magnetization per spin. We'll call this M. And this is basically the average value of the magnetization on a given site, averaged over all sites. Let's say there are n sites in the lattice in total. Now, due to translational invariance on the lattice, we can say that this magnetization is actually just equal to the average value of the spin on any given site. And now I'll just drop the I label and call this the average value of the spin, sigma. And that's just because every site is equivalent to every other site, so I don't need to take the average over all of the sites in the lattice because they're all the same. And this allows us to simplify the form of the Hamiltonian. We can now write it in terms of this average magnetization. And since sigma I and sigma j are equivalent by translational invariance on the lattice, and remembering to avoid double counting of the pairs, we can finally write this Hamiltonian as follows: just over the sum of individual sites where n is the number of nearest neighbours on the lattice, and the dividing by 2 here is to avoid double counting. Of our pairs. So if I sum over the nearest neighbours I and j, and then I reduce this to a single sum over sites I will have counted those twice, so I need to divide by 2. So overall, we arrive at our final result for the mean field Hamiltonian for this spin system, which is some constant shift in energy, n for the number of sites in the lattice, little n for the number of nearest neighbours around each site, times m squared, where m is the average magnetization on the lattice, times the coupling strength J, and the whole thing divided by 2. And then I subtract from this a term which involves the sum over all the individual lattice sites. And it's a sum over the spin of those lattice sites. Remember, sigma I here is plus or minus 1 only for each of the spins on the lattice. And of course, this is a sum over all the sites in the system from 1 to big N. And so this is the model we wish to analyse. It is the mean field Ising Hamiltonian. In particular, note that this term here behaves like an effective magnetic field acting on the spins. It basically biases the energy towards either the up spins or the down spins. And in the end, that's why we end up with a finite magnetization. Now, there's something slightly weird about this Hamiltonian as we've written it down, because the Hamiltonian itself contains M, which is the magnetization of the system. But the magnetization of the system is something that one would find by solving this Hamiltonian and using statistical mechanics. So there's actually a self-consistency equation to this. And what I mean by this is that if we solve this model and work out the magnetization, this M, the result of that calculation, must be the same as the M that we put in the model to begin with. So we'll start with the free energy of this system, which is related to the partition function of the system, minus kBt log z, and we're going to use, of course, the mean field z, the partition function. So this is the free energy. And importantly, the stable thermodynamic phase is found by minimizing the free energy. And what can we minimize it with respect to? Well, we can change this parameter m, the average magnetization in the system. And so we have a condition, which is that df by dm should be equal to 0 in the thermodynamic phase that we're looking for. So what we need is the partition function ZMF. So the partition function of our mean field Hamiltonian is given as the sum over all possible configurations of the system, I'll denote this with this curly brackets, C, of the Boltzmann weights e to the minus beta h mean field, where the beta is the inverse temperature as usual in units of the Boltzmann constant. Okay, so how can we evaluate this partition function? And in particular, we're going to have to worry about doing all of the possible combinations and all the configurations of the spins on the lattice and working out their energy so that we can work out the Boltzmann weights for those. The partition function is the sum of all of those Boltzmann weights. So the first task is to enumerate all of the possible configurations of the system in terms of the spins. But that's actually not so difficult because we just have a plus and minus 1 for sigma I on each of the lattice sites. And so we can write this as the product from all of the lattice sites from 1 to n of the sum over sigma I is equal to plus or minus 1. And then we have the Boltzmann weight. And now we can use the expression for the mean field Hamiltonian given at the top here. And in particular, we see that there are two terms. One is just a constant term. So when I substitute this inside this exponential here, that will be a common factor to all energy terms, and it can be factorized out of the expression. So I'm just going to be left with this term that depends on the individual spin configurations. And what I get is the following. I get a common factor, which is e to the minus beta n m squared j over 2. And then I have to enumerate all of the spin configurations, and then for each of the spins sigma I, it can be either plus or minus 1. And then I have the piece e to the beta n m j times the spin sigma I. And for each value of the spin sigma I plus and minus 1, I have a contribution to this sum. And so I can actually do that explicitly. Where I have the product over all sites in the system, and then for each site of the system, I have the two possibilities, sigma I plus and minus 1, and I can write that simply as 2 cosh of beta n m j. And that's because cosh is e to the x plus e to the minus x, and here the x in question is beta n m j. Okay, good. This looks very complicated, but we're almost there. Okay, because of the translational invariance, every site in the system is equivalent to every other site, and so we can perform this product explicitly. And here we have the final solution for the partition function. Okay, so that was a bit technical and a lot of hard work. If you don't understand all of those steps, then don't worry about it too much. The important thing is that we can find for this system an explicit closed form solution for the partition function. Now we can find the free energy from this, which is just minus kT times the log of the partition function, and take the derivative with respect to magnetization to find the thermodynamic stable phase. So what we want is dF by dm is equal to 0, and we can write dF by dm as minus 1 over beta d by dm of log z, just following from the definition of the free energy. And we've just worked out the partition function. And so this follows as minus 1 upon beta d by dm of the following. We're going to get minus beta n little m squared j over 2. That's our constant shift. And then we have plus n log 2 plus n log of the cosh of beta n m j. Okay, so that looks very complicated, but I hope the logic is clear. And now, of course, we need to take the derivative with respect to m and set it equal to 0. So this is the result, and here you see I've used the fact that the derivative of log cosh is equal to tanh. And this whole thing should be set equal to 0. What does that give us? Well, it tells us that the tanh of beta n m j is equal to m. And so this is the self-consistency equation that we're looking for. and it's a self-consistency equation for the magnetization. In terms of the temperature. Remembering, of course, that beta in this equation is 1 over kBt. So this equation has a hyperbolic tangent involving the magnetization on the left-hand side and also the magnetization on the right-hand side, and that is a transcendental equation that doesn't have any closed-form solutions. However, we can analyse certain important cases to understand what's going on. First of all, let's look at low temperatures. And in fact, let's take the limit of t going to 0. What does that do? Well, as t goes to 0, beta 1 over kBt becomes very large, and so the argument of the hyperbolic tangent becomes very large. The solution to the expression then simply becomes that m goes to either plus or minus 1. If I have tanh of a very large positive number, I get plus 1, and if I have tanh of a very large negative number, I get minus 1. So what we see is that as the temperature goes to 0, the system becomes completely magnetized, and it chooses either the plus direction or the minus direction. All the spins are aligned, either up or down. Another important limit to consider is what happens when the magnetization becomes very small. And we'll do that at finite temperature. What does that mean? It means that the argument of the tanh becomes very small, and this motivates a Taylor series expansion. So we can write that this thing is approximately beta nmj minus, it turns out, 1/3 of beta nmj cubed plus higher order corrections, which we're going to throw away because they will be progressively smaller when the argument beta nmj is small, and that happens when the magnetization is small. And all of that stuff is, on the right-hand side, equal just to the magnetization m. So this is an equation, a polynomial equation in m that we can solve. Remembering that beta is 1 over kBt, we then get the following, where we have a plus or minus sign in front of this expression because we're taking the square root, and I've written beta as 1 over kBt. So this is an expression for the magnetization when m is small. I should say the magnitude of n is small. In particular, it's important to see from this that the magnetization is equal to 0 when kBt is equal to nj, and there are no real solutions when kBt is greater than nj. So this is rather interesting. It tells us that there is only finite magnetization for temperatures less than this quantity n times j, and furthermore, the magnetization vanishes and becomes exactly 0 when kBt is equal to nj. And so this tells us that there's a critical temperature for which the magnetization vanishes. And we call this the Curie temperature Tc, such that Kb Tc is exactly equal to this quantity Nj. So this is the definition of the Curie temperature in this system. It's the point where the magnetization vanishes. And that means that I can write the magnetization in terms of the Curie temperature. T over Tc into the square root of 1 minus T over Tc. So we see that when we're close to the critical point, we have a kind of universal scaling function of the magnetization in terms of a reduced quantity. So let's then write this reduced quantity, lowercase t, is Tc minus T over Tc. This is the proximity of the temperature to the critical temperature in units of the critical temperature. And in that case, the magnetization goes as plus or minus root 3T as T goes to 0. And what we mean by T goes to 0 is the temperature approaches the Curie temperature, Tc. So what we see is the magnetization approaches 0 as the square root of the reduced temperature. So we can put all of this together now and plot what happens to the magnetization in our system as a function of temperature. So let's plot on the vertical axis the magnetization M, and on the horizontal axis the temperature T. What we know is that at 0 temperature, the magnetization saturates to 1. And we also know that at the Curie temperature, the magnetization vanishes. We know that the magnetization approaches 0 as the square root. And if we were to evaluate the whole thing numerically, we would find the full curve, which looks like this. Furthermore, this whole curve can either be positive or negative. We saw that at 0 temperature, the magnetization could be plus or minus 1, and we saw that as the magnetization goes to 0, we have plus or minus square root T. So we can also have the entire curve on the negative side, something like this. And inside here, at temperatures less than Tc, we have a ferromagnetic ordered state with finite magnetization. Whereas outside we have a disordered state with all the spins pointing in random directions and 0 average magnetization. And we see that this is an entropic effect because as we go to higher temperatures, there's a greater favourability for having randomized spins throughout the system, and beyond a critical temperature, all of the magnetic ordering is lost. This is a classical phase transition. What we see is that above the Curie temperature Tc, the magnetic ordering in the system melts. The system itself doesn't melt, it doesn't become a liquid from a solid, but the magnetic ordering melts, so that as we increase the temperature, we have an ordered state going to a disordered state. All of this can be put on a more firm footing in the context of quantum mechanics, and I do this more rigorously in the quantum theory of condensed matter course. It should be noted that the mean field approximation that we used here is only an approximation. However, it does capture qualitatively many of the correct features of the ferromagnetic phase transition. Above the Curie temperature, by the way, we have a paramagnetic state. Rather than a ferromagnet. So now I want to talk about the physical picture for this phase transition. We've just calculated explicitly the phase boundary and seen what happens to the magnetization, but what's going on a microscopic scale? I want to give some sort of physical intuition as to what's going on here. And we'll see, actually, that there are still some surprises. This is a story of temperature, entropy, and the phase transition. If we look at very low temperatures, we see that the magnetization saturates. All the spins in the material are aligned, and the state is highly ordered. It's a ferromagnetically ordered state. So, for example, if I know a spin in one particular place is an up spin, then I can predict that the neighbouring spin is also up, and indeed spins a macroscopically large distance away would also be up. But this ordered state has extremely low entropy. There are not lots of different ways of arranging the constituent parts in the system. I can have all the spins pointing up and all of the spins pointing down. That's a twofold degeneracy, but actually those two different states are separated kinetically by a large energy barrier. So, of course, in nature, we see that the magnetization picks a particular direction and is locked or frozen into that direction, with all the spins pointing in the same direction. Statistical mechanics and thermodynamics tells us, however, that the stability of the phase depends not just on the internal energy, but also the entropy, as I mentioned earlier, and the free energy involves the entropy multiplied by the temperature. So this entropic term becomes important at higher temperatures. So the system chooses a more disordered state at higher temperatures, with more alternatives for arranging the constituent particles as to maximize the entropy and therefore minimize the free energy. But how does it do this? How does it introduce this randomness and this extra entropy? So consider this situation. At very low temperatures, our piece of magnetic material becomes ferromagnetically ordered with a saturated magnetization. That means that all of the individual spins in the system are aligned and pointing in the same direction. Here, for the sake of example, I've chosen that direction to be upwards. But what about at higher temperatures? What are the spins doing at higher temperatures? One possibility is there's just thermal fluctuations where individual spins in the system can take a different orientation. However, careful analysis of the problem, and this is beyond the mean field analysis that we did in this lecture, reveals something different. Actually, we see the formation of magnetic domains. The magnetic domains are regions of the material where all of the spins have perfect ferromagnetic order with aligned spins, but the spin direction can change. So, for example, there might be a certain region of space where all of the spins are still pointing upwards, but in a neighbouring region, the spins might be pointing down or in some other direction. So at finite temperature, below the Curie temperature, the average magnetization, when we average over these domains, is actually less than the saturated value. However, it's still finite, so there's still some kind of overall propensity for the spins to be favouring a certain direction over others. But when we go above the Curie temperature, we have a phase transition to the paramagnetic state. So how does that look? Then all of the spins are totally pointing in random directions, and on average, the magnetization has gone to zero. One way of viewing this paramagnetic phase is that the domains, the size of the domains has shrunk to zero, or the size of the domains has shrunk to the size of a single spin. So each domain has some kind of random orientation, and the domains are only the size of an individual spin, so everything is just totally random. The magnetic ordering has been lost above the Curie temperature, and we can say that the magnetic order has melted. Of course, this is not a structural melting from a liquid to a solid, but it is a phase transition. It happens abruptly at a specific temperature, characteristic of the material. This is the Curie temperature. For example, in iron, the Curie temperature is around 770 degrees Celsius. To understand this, you need statistical mechanics, similar to the structural transitions from solid to liquid in water. And this does not happen gradually, but as a specific point. So below Tc, we have a ferromagnet, and above Tc, we have a paramagnet. We can also think about this in the opposite direction. We can think about starting off at a very high temperature, and then lowering the temperature. And what we'll see is that magnetization spontaneously develops. This happens by tiny domains of spins pointing in the same direction being produced, and then the size of those domains starts to grow, and neighbouring domains coalesce, and eventually you just have one massive domain covering the whole material, with the magnetization saturated at its maximum value. However, aside from spontaneous magnetization, it's also possible to deliberately magnetize a piece of ferromagnetic material by putting it in a strong external magnetic field. Then the magnetization of the material will become aligned in the direction of the field by the kind of mechanisms that we talked about at the beginning of this lecture. So how do we do this in practice, experimentally? Well, the easiest way is to use a solenoid coil wrapped around our block of material. So let's imagine that we have some iron core, some material made of iron. And then we wrap around this material some wire in a coil. And we connect this to a battery. And we see what happens. As we increase the current in this coil, we increase the magnetic field that's inside the solenoid. And as we increase this current, the magnetic field increases, and then magnetization of the iron core aligned with the field will increase. How does this happen? Well, as we put the iron core in the magnetic field, the magnetic domains which are aligned with the field begin to grow, and the magnetic domains that are not aligned with the field begin to shrink, and the magnetic domains eventually coalesce, and the object becomes completely magnetized when we put in a very strong magnetic field, which is created by making a large current flow through the solenoid loop. And provided that our temperature is below Tc, when we turn off the current, the magnetization will remain. If the magnetization was larger due to the presence of the field than it would have been at that temperature due to the spontaneous magnetization, then the magnetization will relax to its zero field value. However, that zero field value, when T is less than Tc, is not equal to zero. Indeed, if we reverse the direction of the current, we reverse the direction of the magnetic field, and therefore the magnetization will be reduced, and it is possible to bring the magnetization down to zero using a current that's pointing in the opposite direction. Indeed, if we continue to increase the negative current, we will be able to reverse the direction of the magnetization. If we then switch off the magnetic field, it will relax to a finite value, but negative of what it was before. So altogether, this gives us a hysteresis loop. Let's now make a plot of the magnetization as a function of the current through the solenoid for the case when the temperature T is less than the Curie temperature Tc, so that the system can retain a magnetization. We'll see that the magnetization of the material at a given current strength depends on how the material got to that condition. So first of all, let's imagine that we have an unmagnetized piece of iron. It's zero current, and it has zero magnetization, so it sits at the origin of this graph. Then, as we increase the current, magnetization develops in the material and saturates at very large positive currents to some particular value. Now let's say that we reduce the current, we start to switch it off. The magnetization will reduce, but it will not reduce all the way to zero, because for T less than Tc, the magnetization of this ion can be finite, and so the magnetization reduces, but not all the way to zero, but rather to some finite value, which is characteristic of the temperature that we're at. Indeed, to bring the system back down to zero magnetization, I would actually require to apply a negative current in the opposite direction. But if I continue applying the negative current and make it stronger and stronger and stronger, then obviously I will saturate the magnetization to its maximum possible value in the negative direction. And then we can play the same game by slowly decreasing the magnitude of the current flowing in that direction. And what we'd see is that the magnetization, the magnitude of the magnetization, again decreases, such that when we have zero current, we have a finite magnetization. Now this would be the opposite sign of the magnetization when we came from the positive current side. To bring the magnetization of the material down to zero, I have to apply a positive current. And again, it's the same deal. As I increase the current, now the magnetization will saturate back up to its maximum positive value. And so overall, I have a loop like this, where it depends on the path taken as to what the magnetization ends up being. And this whole thing is called a hysteresis loop. So this concludes our discussion of magnetic materials for this course. The physics of magnetic materials is a wonderfully rich and diverse topic, and there's much more to say about this, especially from the quantum mechanical side, but in this course in electromagnetism, we'll leave it at that. So the last thing I need to tell you about in this part of the lecture course to do with magnetostatics and materials is how Maxwell's equations and our theory of electromagnetism has to be modified when we're considering magnetic fields in matter. Whether we have a ferromagnetic material or a paramagnetic or a diamagnetic material, magnetized objects produce their own magnetic field that must be taken together with the external magnetic field when using Maxwell's equations. So the logic here is very similar to how we discussed dielectrics for electric fields in materials, and so I won't go into a great deal of detail on this, but I want to sketch the basic ideas and present the main equations. So here we see that the total magnetic field is the sum of the applied field and the induced field, which is the field due to the material's response to the applied field. Now, in general, there is a complex feedback here, because the total magnetic field causes or affects the magnetization of a material, and the magnetization of the material in turn affects the total field. The good news is Maxwell's equations still hold, but this is for the total magnetic field rather than just the applied magnetic field. So how can we take into account the material's response when using Maxwell's equations? Well, let's start with the definition of the vector potential for a perfect magnetic dipole. This is something that we worked out in a previous lecture. We have that the vector potential A at a position in space R is given as mu0 over 4 pi multiplied by the magnetic dipole moment m crossed into the unit separation vector divided by the separation vector squared. And remember here that this separation vector is r vector minus r primed. This is the field point where we're trying to evaluate the vector potential, and this is the source point, which is the location of our perfect magnetic dipole. Okay, so that's the vector potential for a perfect magnetic dipole that we worked out in the last lecture. So let's remember that we have a magnetization field in a material which we imagine to be consisting of a load of perfect magnetic dipoles in a sort of continuum smeared over the whole system. So we define the magnetization field M such that the magnetic dipole M is related to the field M by integrating over a small volume element, d tau. So we sort of elevated the individual perfect magnetic dipoles at individual points in space to a sort of continuum field, and that's a vector field which we call the magnetization field. So if we want to know the vector potential due to an entire magnetized object, such as a piece of ferromagnet or whatever, then we need to integrate all of these perfect magnetic dipoles over the whole material. So we write that our perfect magnetic dipole moment is the magnetization field d tau, and then we integrate over the volume d tau. And now we can manipulate this expression a little bit by using some old tricks that we learnt in studying dielectrics, which is that if we take the gradient of 1 over script r, and I'm taking the gradient with respect to the primed coordinates, this actually is equal to script r unit vector divided by script r squared. And that's exactly the object that we see inside the integrand here. So if I use that identity, and then I integrate by parts, then I can rewrite the vector potential as the sum of two terms, a volume term and a boundary term. Let's see how that looks. We find that the vector potential evaluated at a point in space r can be written as mu naught over 4 pi times the volume integral of something we'll call the bound current density evaluated at a point r primed divided by script r and then integrated over the volume d tau primed, plus another contribution, mu naught over 4 pi, but this time we're integrating over the surface, which is bounded by this volume. And what we're integrating in that case is a bound surface current density evaluated at r primed divided by script r, and then integrated over the surface. In this expression, I have introduced and defined the bound volume current density which is JB, and that follows from our calculation as the curl of the magnetization field. I also introduced the bound surface current density, which is this KB, which is given as the magnetization field crossed with the unit vector normal to the surface of the material. So the conceptual simplification here is that instead of calculating the field due to the material's response directly, we replace this with the field due to these bound volume and surface current densities. So the magnetic field that's due to the magnetized object is entirely equivalent to some bound current density and some bound surface current density. And these things are both related to the magnetization field M. And actually, we can already learn something about the bound volume current density, JB, because it's defined as being the curl of M. And therefore, we know that the bound volume current density must be divergenceless. And that's written mathematically as del dot JB, which by the definition is the divergence of the curl of our magnetization field. And of course, that has to be equal to 0 because the divergence of the curl is equal to 0 automatically for any vector fields. So, we've learned something already just by the mathematical structure of this problem, that we can have a bound volume current density, which we call JB, but that it has no divergence. Okay, what about our Maxwell's laws? For example, what about the Ampere law? This still holds. So Ampere's law in differential form tells us that the curl of the magnetic field is related simply to the current density. This is magnetostatics. In the dynamic case, there's an extra term, but we're just talking about time-independent phenomena here. So this still holds, but as I mentioned, the current density J is the total current density, which is the free current density plus the bound current density as written above. And when I say free current density, I mean the current density in the rest of the world that's giving rise to all of the magnetic fields that is causing the magnetization of the object in the first place. So the free currents are the things that we know about and can control, and the bound current densities are the material's response to those free currents. And it's the total J, the sum of those two terms, that enters in Ampere's law. So if we do a bit of rearrangement, we can write that 1 over mu naught of the curl of B is equal to the free current density plus the bound current density in a material. And the bound current density can itself be written as the curl of the magnetization field. And so this allows us to formulate Ampere law in a slightly different way. We can write it as the curl of something I'll call H. And that's going to be just equal to the free current density that we know about in the world and can control, and doesn't make any reference to the induced field of the material and the induced bound current density from that. Here I have defined that this H object is 1 over mu naught times the actual total magnetic field minus the magnetization. So this is kind of playing the role of the electric displacement in the theory of dielectric materials. Just as we derived Ampere's law in integral form, which we found to be very useful previously, we can do the same thing here. We can take this equation and use some of the results of vector calculus to relate this to the integral around a closed loop of H dotted into the line element dl integrated around a loop. This will be equal to the enclosed current, but in this case, specifically the enclosed free current. So again, this is a nice formulation because it only makes reference to the free currents rather than the bound currents. Let me make one final remark on linear magnetic materials. These are materials where the magnetization is linearly proportional to H. And if we just substitute in our definition of H, then we can write that the magnetic field, the total magnetic field B, is just given by H plus M. And that in turn can be written as H plus chi M times H, which can be factorized out. So we see that the magnetic field B is proportional to H. This object chi M here is referred to as the magnetic susceptibility. And we can then combine all of this stuff into the definition of something mu, which we call the permeability. So that overall we have that B is equal to mu H. For linear media, we also see that the bound current density JB, which is the curl of the magnetization, can be written in terms of the curl of H. And the curl of H is, of course, from Ampere's law, just the free current density. So we see something interesting in linear media, that the bound current density is actually proportional to the free current density. If in a given region of space there's no free current density, then there can also be no bound current density. So what we see here is that the usual theory of magnetostatics that we studied at length in the last lecture can still be applied. We just have to use this concept of H rather than of the magnetic field B, because it incorporates not only the applied magnetic field, but also the magnetic field due to the material's response. In the case of linear magnetic materials, which many materials are, especially at weak fields, it all becomes very simple because the magnetic field B is proportional to H, and in fact the bound currents are proportional to the free currents. So I hope this lecture was useful. We talked about magnetic materials, we talked about paramagnets, diamagnets, and ferromagnets. We talked about the spontaneous magnetization of ferromagnetic materials and the phase transition through the Curie temperature and the hysteresis loop on applying a magnetic field to a ferromagnetic material. We also discussed how Maxwell's equations get modified when we're near or inside a magnetic material that can be magnetized in the presence of an external field.